In this video, we're going to switch gears and we're going to start to talk about equations. All right. So everything that we've done before has dealt with expressions, right? Just changing, simplifying, adding, subtracting, multiplying, and dividing different types of algebraic expressions. Now, what we're going to do is we're going to look at equations. And so basically, an equation is a statement indicating that two algebraic expressions are equal to each other, right? So we can take two polynomials, set them equal to each other, and that creates what we call an equation, right? So an equation starts out with an equal sign. And so I'm going to write a very simple equation here, something like x minus 7 equals 2/3, right? That is an example of an equation. It has an algebraic expression, a linear algebraic expression, x minus 7 on the left-hand side, and it has a constant polynomial, which is an algebraic expression, which is 2/3 on the other side, right? Our goal in this chapter is to be able to solve different types of equations. In this section, in this video, we're going to talk about linear, rational, and absolute value. All right. Solving equations involve the process of finding solutions. Well, solutions are the value is a solution is the value, or solutions are the values that satisfy the equation. That means if I plug them into the equation or substitute them in everywhere I see my variable, I get a true statement that both sides are equal. All right. And so usually when we go through the process of finding the solutions, we solve equations, we use properties of equality, right? There are two properties of equality that we generally use. We have the addition property of equality, and we have the multiplication property of equality, right? And that basically says you can add the same thing to both sides and you will still have an equivalent equation. And you can multiply both sides by the exact same number, except if you multiply by zero. We don't like to multiply both sides of an equation by zero, okay? But if you multiply both sides of an equation by the same number, then you'll have an equivalent equation in the next step. All right. Now, there is no subtraction and division property of equality. However, we still subtract and we still can divide both sides by the same number as long as we don't divide by zero and still have an equivalent statement, because subtraction is the same thing as adding the opposite and division is the same thing as multiplying by a reciprocal. We just don't have a division or a subtraction property of equality. Not only do we use these properties in order to help us solve equations, we also use properties of real numbers: the distributive property, the commutative property, the associative property, additive inverse, so on and so forth. And so we're going to go ahead and start to talk about solving different types of equations. Let's start with linear equations in one variable. Linear equations in one variable, these are equations that can be written in the form. Anytime you see can be written in the form mathematically, it means you can write it so that it looks like this in general. And so we have ax plus b equals 0, where a and b are real numbers such that a does not equal 0. Basically, we have a variable x that's written to the first power. This x is not under a radical because the power would not be 1. This x is not raised to another power other than 1. And this x is not in a denominator because that power on that x would not be a 1 any longer. All right. It'd be negative something. All right. And so as long as we can write it like this, it is a linear equation. All right. Now, I have 4 linear equations here. They don't look nothing like what we have right here, right? But we could rewrite them in a way so that they look like this, and that makes it a linear equation. We just want to see x to the first power where it's not under a radical, not in a denominator, okay? And not within some function like a logarithm or exponential function or a trig function, all right? And so let's go through this process here to solve these equations here. In fact, what I want you guys to do is I want you to solve these on your own because I know you are good at doing that. I'm going to say that this one equals x equals 11. I'm going to have you solve this one on your own by yourself. Remember, this is a solution. We can write it as a set or in set notation. Since it's an element with one element, a set with one element, then I can write it with the squiggly bracket, and I can say that my solution set involves this number here, which is x equals 11. And in general, linear equations have one solution in general. We're going to look at this second one together because I want to show you something that we'll use when we solve rational equations. I have x over 4 minus 3 equals x over 2, that's a 2 there, plus 3. Now, I'm going to do something that you may not do. What I'm going to do is I don't want to work with these fractions here. And so since I don't want to work with these fractions, I'm going to find my lowest common denominator. I have a 4 in this denominator. I have a 2 in that denominator. My lowest common denominator is 4. And what I'm going to do is I'm going to multiply both sides by the LCD. Now, you may ask, Mr. Pompey, why are you doing that? And I'm going to tell you why, right? When I do that, since there's more than one terms on each of these sides, I have to use my distributive property. Well, 4 times x over 4, the 4's cancel, and I'm just left with x. And 4 times 3 is 12, so I get x minus 12. When I distribute on this side over here, 4 times x over 2, well, 2 goes into 4 twice, so I get a 2x. And then 3 times 4 is 12. I'm going to bring my variables on my right-hand side, so I'll subtract x from both sides. You don't have to write this like this. I'm just going to do this here today. And then I'll subtract 12 from both sides. I get negative 24 equals x. Notice here, when I multiply both sides by the LCD, I was left with an equation that no longer had fractions, right? So this gives me a way, multiplying both sides by the LCD gives me a way to get rid of my fractions, to clear my fractions out of an equation. All right, and that's what a technique that we're going to use later, all right? And so, but this is what we have here. We have x equals negative 24. I can write that as a solution set like that, right? And so I've solved that equation there. This next equation, let's look at it. I'm going to first start by using my distributive property. So I'm going to distribute my 2 to the x, I get 2x, and 2 to the 1, I get 2. And I get 2x plus 2. I'm going to pick my x's to be on my left-hand side, which means I got to get rid of the 2x on my right-hand side. So I'm going to subtract 2x from both sides. When I subtract 2x, they cancel to 0 there, they cancel to 0 there, and I get 2 equals 2. Well, it just so happens that 2 equals 2 is a true statement. This is always true. In fact, this equation is going to be true no matter what x value I plug in, because although it looks different in the first step, it's identically the same in the second step right here, right? 2x plus 2 definitely equals the identical expression 2x plus 2, right? And so my solution here would be all real numbers. That is my solution set. Let's go to part D here. I have 2x plus 3x, which is 5x. Let's combine those terms. I have a 5x plus 1. If I get my x's on this side, I subtract this 5x, but I got to subtract it on this side as well. And I'm going to get 0 equals 1. This is never true. And so since these are equivalent statements, right? So this means that this equation here is never true, no matter what x I try to plug in. And so I don't have a solution here, right? And so my solution we can call our empty set, right? Remember we said this symbol here was the empty set. And so sometimes our linear equations have one solution that's here and here. Sometimes they have infinitely many solutions. That means it's all real numbers. And sometimes it has no solution. And we have names for terms that we use for these several cases. All right, an identity equation is an equation that is satisfied for every real number, right? And so this example C here would be considered an identity. And so an identity, no matter what value you plug in for x, it's going to work. It's going to be a solution to your equation. A conditional equation is an equation that is satisfied by at least one, but not every real number, right? And so this one is not even satisfied by any real number, so that's not conditional. These two are conditional. So B and C are considered conditional. All right, it doesn't have all real numbers as the solution. It has a single solution here and here. So these are conditional equations. And then an inconsistent equation is an equation that has no solution. And so part D will be considered inconsistent. Just some vocabulary terms to get your head wrapped around solving equations. Let's look at the next type of equation, rational equations. All right, rational equations are equations that contain rational expressions, right? And I basically like to say that a rational expression is one where a variable is in the denominator, right? And so we have these examples here, right? Notice here we have an x in the denominator. Now, our goal is always to find all the solutions, right? When we were dealing with our linear equations, our goal was basically to isolate x, your variable x, right? In isolating x, you can use your addition property of equality, your multiplication property of equality. You may have to use your distributive property, like in this example, and subtract, multiply, divide both sides by something to get x on one side by itself, all right? When we start having different types of equations, you have to start to think about, well, where's x and how do I get it from being there and then what steps can I take to get it to be isolated, right? Now, sometimes we're going to have x on both sides, right? But when we have rational equations, we got to think about something being in the denominator, a variable being in the denominator. And we don't want to be able to solve that equation with the variable in the denominator still in our answer, right? So we got to find a way to get the variable out of the denominator. So one of the goals here is to get the variable out of the denominator, okay? And one way to get the variable out of the denominator is to clear the fractions. And one of the ways to clear the fractions, if you go back up to what we did before, is you multiply both sides by the LCD, right? And so that's the technique we're going to take to solve our rational equations here. We're going to multiply both sides by the LCD of all of the rational expressions. Then we're going to that's going to clear all of our fractions, and we're going to solve the resulting equation. And then we're going to check that the solutions are in the domain of the rational function. Now, we hadn't talked about domain yet. What we're going to do is we're going to check that the potential solution, all right, I'm going to write some stuff, doesn't make the denominator equal 0. That will make the expression undefined. Remember, we can't divide by 0. So if we get an answer such that if we plug it into one of these denominators, it makes that denominator 0, then it can't be my solution because it'll cause my expression or my equation to be undefined, right? And so we don't want that to happen. And so let's look at some examples of where we solve these equations here. To solve each equation, identify each equation as an identity, inconsistent equation, or a conditional equation. Let's look at this first example. I have 4 over x minus 1 minus 9 over x plus 1, and that equals 3 over x squared minus 1. I'm going to find the LCD, right, because I see a variable in my denominator. Now, to find the LCD, we've got to factor. All right, I'm going to need a lot more space here. So I'm going to factor my denominators. That one's already factored, right? And I'm going to have over 9 over x plus 1. That's factored. And that's going to equal, I can factor this denominator here, x plus 1 times x minus 1. Now we want to find our LCD. I'm going to come over here. My LCD, well, this one has an x minus 1 in its entire denominator. This one also has the x minus 1. So if I put the x minus 1 in that denominator, I've taken care of that, and I've taken care of that. I also have this denominator, which has an x plus 1, and that takes care of this denominator. But this one also has an x plus 1, so it takes care of that. So I have x minus 1 times x plus 1 is my LCD. And what I'm going to do is just like when we did this linear equation above here, right? We looked at our denominators, we found that our LCD was 4, and we multiply both sides by that LCD. So what I'm going to do here is I'm going to come and I'm going to multiply both sides by x plus 1. I'm writing it slanted, sorry, times x minus 1. When I do it to the left-hand side, I have to use my distributive property. Now look what happens. This is a 4 over x minus 1. I'm going to multiply this, the x plus 1 times x minus 1, right? It's like it's going to sit on that numerator with that 4 there. So it's going to be like a 4 times x plus 1 times x minus 1. Well, the x minus 1s are going to cancel, so we're just going to have a 4 times an x plus 1. Then when I distribute it to the second term, because I have a minus there, so I got to use my distributive property, that x plus 1 and that x minus 1 are going to sit on top with that 9, and I can cancel the x plus 1s. And so I'm going to have a minus 9 times x minus 1. And on my right-hand side, I have one single term. It's like this thing is over 1. And so if I cancel, I can cancel the x plus 1s and the x minus 1s, and I'll be left with a 3 on my right-hand side, right? And now if I look at this, I have an equation. It is linear, right? Because if I distribute the 4 here, I'm going to get a 4x plus 4. I distribute the negative 9, right? So that's a minus 9x plus 9. And notice this is to the first power, that's to the first power. That's how I know it's linear. Well, I can combine the 4x, that's a 4 by the way, and minus 9x, so that's a negative 5x. And the 4 and the 9 are 13. Subtract 13 from both sides. Divide both sides by a negative 5. Same thing as multiplying by a negative 1/5. And I get x equals a positive 2. What I always have to do is to check my solution because I don't want to divide by 0. Now, what I can do is I can go back to my original equation, plug into every single thing and simplify it. Plug into everything, 2 into each of these x's here. Okay. Now, I'm confident in this work that I did, right? So I'm going to kind of cheat and make sure that this possible solution is in fact the solution by just plugging it into the denominator and making sure that it doesn't equal 0. So I'm going to go to this denominator here, plug in 2 for x, I get 2 minus 1, that's 1. That's not equal 0, so that's okay. I go to the second denominator, x plus 1. When I plug in 2 for x, I get 2 plus 1, which is 3. That is not 0, so I'm not dividing by 0 in that expression. And in here, I plug in my 2 here, I get 4 minus 1, which is 3. That is not equal to 0 either. So I'm quite sure that my solution is x equals 2. All right? And so since I got one solution here, this is a conditional equation. All right? Let's look at this next example. All right, we see this equation here. It has an x in the denominator. My goal is to get the variable out of the denominator by clearing my fractions. In order for me to clear my fractions, I need to find my LCD. Well, my LCD in this example is x plus 1. And so since my LCD is x plus 1, I need to multiply both sides by x plus 1. Now I'm going to write all of this out. They cancel on my right-hand side, so I get 11 minus 2x. Over here, I have to use my distributive property. Well, when I distribute it to that first term, I'm just going to be left with a 3x because the x plus 1s cancel. And when I distribute to the second term, I get that right there. So I have 3x minus 5x minus 5 equals 11 minus 2x. Notice I have a linear equation here. Uh-oh, I can combine these two like terms here. Negative 2x minus 5 equals 11 minus 2x. Let's add 2x to both sides. Oh, shoot. What's happening here? When I add 2x to both sides, they cancel here. I get negative 5. They cancel there. I get 11. This is never true. So my solution set is the empty set, which means there's no solution. This equation is inconsistent. All right. So that's the technique that we'll use to solve these rational equations. Multiply both sides by the LCD to clear your fractions, and then you'll come up with an equation that is a little easier to solve. Let's look at another example here. All right, let's get to it. The last type of equation we're trying to solve. All right. Absolute value equations are equations that contain variables within the absolute value. For instance, if I had absolute value of x equals 3, all right? Well, let's reason through this. We know the absolute value represents the distance x is from 0, right? And so basically, I want to solve for x here. If I want to solve for x, I have to find out which numbers on my number line in my real number system are 3 units from 0, right? That's basically what this is saying in words. And so you could draw a number line, Go 1, 2, 3 units to the right and you get to 3. And if you go to 3 units to the left, you get to -3. So your solution is basically x equals plus or minus 3. That is how you can solve an absolute value equation, right? But we're not going to do the number lines, and it's not going to be this simple with just an x in there, right? And so there's 3 cases. Let's assume that we have some constant a that's a positive number. Whatever's in this absolute value, notice I have an uppercase X here to represent any algebraic expression. If I want to solve this, I take whatever algebraic expression is in that absolute value, and I set it equal to the plus or minus of that value A there, just like I did in this example here. Because you're going to be A units to the right of 0, I like this 3, so you're going to be A units to the right of 0, and A units to the left of 0 is going to get you to the negative A. So whatever is in the absolute value is going to have to equal the positive and negative of that. And so what we usually do is we set whatever's in the absolute value equal to the positive, and we come up with another equation by setting whatever's in the absolute value equal to the negative, all right? If this were 0, this will only be one equation, right? Because 0 is 0 units from itself, right? And so in these types of equations, we only have one. There's no need to put a plus or minus because 0 is neutral. And so we take whatever is in absolute value, set it equal to 0, and solve that. Here we have absolute value of some algebraic expression equals a negative number. And when that happens, we know that there is no solution, because absolute value represents distance from 0, and distance from 0 is never going to be negative. And so this is always inconsistent. And so if we look at this example here, before we get to the example, our goal is to really look at each of these here. I want to make a statement here. Notice each of these have an absolute value of some expression. That's why I use this capital X again, of some expression. It may be like this, a 3x plus 4. All right. But notice the absolute value is always on one side by itself before I take the absolute value off and, for instance, put this plus or equal to plus or minus A. All right. Remove the absolute value. It's in isolation on one side by itself and 0 is on the other. And that's how I drop the absolute value in that case. And this one doesn't have a solution, so we won't talk about that. But one of the points I'm trying to make here is that the first thing you need to do is to isolate your absolute value expression. Get it on one side by itself. Then you follow one of these cases here to drop your absolute value symbol, because we can't solve for x if it's in the absolute value. So our goal is to drop the absolute value, and these 3 methods are how we're going to do that. And so in example 3, it says solve each equation. Here we have absolute value of 3x plus 4 equals 12. Well, it's already isolated, and I'm in this case right here. So that means the 3x plus 4, now if you wanted to write this, you don't necessarily have to write this, equals plus or minus 12. Sometimes when we put this plus or minus, it can get confusing. And so what a lot of people like to do is say, oh, I know it's going to equal to the positive 12, and then I know I'm going to get my other solution by setting it equal to the negative 12, right? And I have 2 equations to solve, and I have 2 solutions. Subtract 4 from both sides, divide both sides by 3, we get 8/3. We go through the same process on the right-hand side, we get negative 16/3. So our solution set is this. Let's go to part B. Now, this is one of the cases where it's not isolated. I have absolute value that's multiplied by 3, and there's a 5 added to it, right? I'm going to isolate it by starting by subtracting 5 from both sides. We can divide both sides by 3 to get rid of that 3 there. I don't want to distribute because my distributive property doesn't apply to absolute values. So we're going to divide both sides by 3, and I get absolute value of x minus 4 equals negative 5/3. And you may have a natural inclination to do exactly what you did over here. All right, but we did this because we have a positive number over here. Notice I have my absolute value on this side, and I have a negative number here. In this case, we have an inconsistent equation because an absolute value should never equal a negative number, right? And so there's no solution here, and we can identify this equation as inconsistent. All right. And that concludes this video. We'll see you next time.